So in the last video, we defined what it meant for a graph, or for two graphs to be isomorphic to each other. And we had said it really means that those two graphs are structurally the same. They have all the same kind of basic structural properties, but the way that we technically defined it is we said that G is isomorphic to H if you can find some isomorphism phi from G to H, or technically from the vertex set of G to the vertex set of H that preserves edge relation. In other words, if you can find a bijection from one vertex set to the other, so that if you have an edge in this first graph, its image is also going to be an edge in the second graph. And so we found that it's kind of tedious to find that bijection itself. And if you're just kind of handed two graphs and you're trying to determine whether they're the same graph or not, it's useful to have some tools to try and help you figure out whether they're actually even isomorphic to each other without finding the isomorphism, right? Or another way of saying that is, if you're given two graphs and you're trying to figure out whether they're isomorphic, to prove that it's not isomorphic, you don't want to prove that no isomorphism exists. That's hard to do. But if we know certain properties of an isomorphism, and we can prove that that graph doesn't have that property, then that's an easy way for us to say, oh, there's no way these two graphs are isomorphic to each other. All right, so let's notice some observations based on this definition. First of all, this function phi, this isomorphism function from the vertex set to the vertex set of G to the vertex set of H is a bijection, which means it's one-to-one and onto. And since we're only really looking at finite graphs, what this means is that you have to have the same number of vertices in G as vertices in H, right? So G and H must have the same order That's just a way of saying the cardinality of this set is equal to the cardinality of this set. And since this bijection has to preserve the edge relation, right, any edge in G has to map to an edge in H and vice versa, well, that means that they have to have the same size as well. They have to have the same number of edges. So G and H have the same size. All right, why is this useful? Well, this is a quick way if you're looking at two graphs and you notice that one of them has more vertices than the other, or one of them has more edges than the other, then you know right away there's no possible way that they could be isomorphic. Okay, some other observation. Adjacent pairs of vertices in G have to map to adjacent pairs of vertices in H, and so this can be a helpful tool for determining where two graphs are not isomorphic if you know for a fact that one vertex in one graph has to map to another, but maybe there's some reason why you end up with a pair of vertices that are adjacent in one but not in the other. Then you can be sure that that those graphs are not isomorphic to each other. All right, and using that reasoning, if the degree of a vertex V in the first graph is equal to K, well, that means that there's K other edges that are adjacent to it or incident with it, which means when you look at the image of that vertex, right, phi of V, that's a vertex in the second graph, the degree of that vertex has to also be equal to K. Remember when we looked at that last example, or when we looked at the first example, I should say, the first thing we did is we said, well, these two vertices have to be the same as each other since they're the only vertex in the graph of degree 1. Right? So if you knew, for instance, that one of your graphs has a degree 1 vertex but the other one does not, then there's no possible way that it could be isomorphic to each other because the degree of a vertex in the first graph has to be the same as the degree of its image. And the other thing is that you can prove that an isomorphism is actually an equivalence relation on the set of all graphs of a particular order, and you'll prove that in the exercises. So how do you know when two graphs are isomorphic? Well, one thing you can do to try and get an idea of whether they're isomorphic or not without first trying to jump into forming the isomorphism is to ask yourself the following questions. First of all, do the graphs have the same size, the same number of edges? Do they have the same order, the same number of vertices? Do they have the same degree sequence? Do they have the same number of components? If the graph is a disconnected graph, they would have to have the same number of components. And do the graphs have some common property or characteristic? Like, can you show that both of the graphs contain a particular k cycle or a particular path of length k, or do they have the same diameter? And if the answer to any of these questions, if any answer is a no, the graphs are not isomorphic. Now that doesn't mean that if the answer is always yes, that they're necessarily isomorphic, right? Because you can't really list all the different properties, but it just gives you an idea of whether they are not isomorphic, right? There's no work to do if they're not isomorphic. If they are isomorphic, well, then you have to actually find that isomorphism between them and show that it's an isomorphism. Okay, so let's look at just a couple of examples here. Given these graphs G and H, for each of these three examples, are they isomorphic or not? So one thing that we might start off by doing is finding the order and the size and the degree sequence of each of these graphs. Well, this first graph has 6 vertices, so the order is 6. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, has size 9. And its degree sequence, you'll notice that the degree of every vertex is 3. 1, 2, 3, 1, 2, 3, 1, 2, 3, 3, 3, and 3. So the degree sequence is 3, 3, 3, 3, 3, 3. Well, okay, that's all true here as well. It has 6 vertices, it has 9 edges, and its degree sequence is 3, 3, 3, 3, 3, 3. So it's the same for both graphs, which suggests to us that it might be isomorphic, but if you try to start finding an isomorphism, you're going to have a bad time. It's not going to work out for you. And so what it can be helpful to do is look for some property that one of these graphs has that the other one doesn't. And in particular, you might notice that this second graph here, we have a name for it. We call this the K3,3 graph because there's 3 vertices up here, there's 3 vertices down here, and you have every possible edge connecting this first set to the second set. But in particular, there's no edges connecting any vertices in the top row to each other or any vertices in the bottom row to each other. That is to say, there's no triangles here. There's no 3 cycles. There's no odd cycles at all. This first graph G certainly has 3 cycles. In fact, it has 2 of them. But this graph here, K3,3, has no odd cycles. So there's no triangle graph here. So G has a 3 cycle, but H does not, which means G is not isomorphic to H. Right? There's no need to go through that work of finding an isomorphism because they're just not isomorphic to each other. All right, for number 2, we try something similar. We've got the order is the number of vertices. There's 8 vertices. The size is the number of edges. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the degree sequence, let's see, this is degree 3, this is degree 3, 3, 3, 2, 2, 2, and 2. So the degree sequence would be 3, 3, 3, 3, 2, 2, 2, 2. And you can go through here and try the same thing. You're going to find it has the exact same order, the exact same size, and the exact same degree sequence. This one's starting to look like maybe it could be isomorphic. They both have this 4 cycle here. They have a 4 cycle on the outside. Are there other cycles? Well, you can try and play around with it and see if you can find a cycle that this has that this one doesn't. But another thing to notice is that our degree 3 vertices here all form a 4 cycle. Right? Together they're all connected to each other in a 4 cycle. Here, our degree 3 vertices do not form a cycle. Right, here's our degree 2 vertices and our degree 3 vertices. This isn't a cycle here, right? You can't, go in a cycle and visit all 3 of the degree 3 vertices and come back again. So this is sort of a structural element that G has that H doesn't have. Another way of saying that is if there was an isomorphism phi from G to H, the degree 3 vertices of G must map to the degree 3 vertices of H. Right, so these three in some order would end up getting mapped to these 3 vertices here. Whoops, this is 2. But the problem is these 4 vertices here form a 4 cycle, but in G, these 4 vertices form a 4 cycle, and they do not in H. So there's no way that that isomorphism could actually preserve the edge relation, because you'd have to have these 4 edges making a cycle, and you don't even have 4 edges between them here. So this could not actually be an isomorphism. It's a contradiction, and so G is not going to be isomorphic to H here either. And for this last example, I'll let you copy it down and try it yourself. See if you can figure out whether these graphs are isomorphic to each other. Either find an isomorphism between them, find some labeling here and a labeling here such that it preserves the edge relation, or explain why these graphs are not isomorphic to each other.